Okay, good afternoon. Let's start lecture. So let's talk about welded design today. This is lecture 21 actually. Okay. So I'll give you a short introduction to welding and the welded joints, and basically we'll look at some terminologies, particularly related to welding symbols, okay, used in communicating of specifications. And then we'll look at how to calculate stress on the welds and the welded joints, okay, and basically in terms of design and analysis of welded joints. Okay. So looking at the generic diagram right here, and we are right now at this location. Okay. So, a couple of concepts: weld, joints, and weldments. Okay. Weld means it's a zone of metal. It joins two or more components created by localized melting, mixing, and cooling a metal from a parent component and expendable filler metal. So basically, you are melting the parent metal and some kind of filler material together, okay, to join them as a different kind of type joint types there. Okay. The joints basically we'll look at different kind of joint type. Okay. It's basically a configuration for parent components defining a gap to be filled by a weld. And weldment, it's a concept referring to the structure of the components, okay, constructed by welding several components together. And here's an example of a weld in the joints. So this is basically a weld here, and the joint here is called the T-joint here because it's basically look like a T, right? And what you do is you basically fillet welded here, okay, and fillet weld at the bottom there. Okay, yeah. Okay, so. And this is another example. It's a digging machine, and you look at the arm at here, and also including the digger here. So they're basically welded everywhere, right? It's the welding. It's a typical weldment. Okay, so it's a structural, right? Structural component. The welding process. Okay, this is generally a very common topic if you go to college and learning, particularly if you're trying to pass exam of welding certificate, right? They're all called arc welding, right? And arc welding is you use a power supply to create an electric arc between the electrode and the parent metal, and the electric arc, okay, will cause a very high temperature and will cause melting the metals at a certain point, right? And then you joining those things together. In terms of categorizing this process, we can use the following two. We can either call it consumable electrode method or non-consumable electrode methods. Okay. So consumable electrode methods, okay, there's typical two at here. One is called shield metal arc welding. Okay, this is the mostly widely used, and it's old type. It's called stick welding. Okay, basically you see the picture, people holding like a gun type things, and there's a filler material like stick, okay, sticking out, and then you're going through this metals, right, to do the welding. Gas metal arc welding, okay, and that's also consumable electrode methods. Okay. But in this particular case, they use a continuous wire feed. Okay, I'll show you a picture next. Okay, as electrode. So, and then there's some inert gas, okay, to shield the metal and the weld, okay, from contamination. Non-consumable electrode method, that's essentially there's one called tungsten inert gas, TIG, okay, TIG weld. Okay. TIG weld is very useful. It can be used on almost all different kind of metals. Okay. So we'll look at a couple of pictures relating to these two different methods. So the first one is the stick weld, okay, shield metal arc welding. Okay. Okay, this is the most common one. Okay, it accounts about 50% of all industrial weld. The stick here, basically, there's a coating outside the stick. Okay, the coating here, they call it flux. Okay, so inside here is the core, and that's basically the filler material. Okay, so when you do the welding, the heat will melt the flux, and the flux basically will cause a protection shield from protecting the welds from oxidation. Okay, the shortcoming is it'll form a so-called solidified slag. Okay, as you are going along this the metal here, so the slag needs to be scraped off after the welding. Okay, yeah, so that's stick weld. Okay, and there's power going through the electrode and then cause an arc. Okay, things like that. Here's another picture, basically doing this, talking about the same thing here. Okay, so that's the inner side is the core material. Okay, and outside of the flux. Okay. The gas metal arc welding. So there's a wire, automatically wire feeding, okay, through here. So it's not a stick, basically it's automatic wire, and the wire is basically electrode. And then there's this gas here. Okay, it is basically or helium gas or any other inert gas. So the inert gas will be applied to the welded joints here, and to basically propel all the oxygens or nitrogens, out of the location at here. Okay, yeah, and that's another picture showing this welding process. So the feeding wire is the 3 at here. That's the electrode. Okay, yeah. Okay. TIG weld, the gas tungsten arc weld. This one, basically they use a non-consumable electrode. It's a tungsten. Basically, the electrode here is a tungsten. Okay, yeah, and there is shielding gas coming from here. Okay, and then your filler material, okay, or filler rod, okay, it's a separate stick. Basically, you can hold a gun here and then hold this filler rod on the other hand, and it's going along this weld here, right? Yeah. If you watch the YouTubes, you'll see many tutorials, teaching you how to hold it properly to have a proper, basically, weld. Okay, so basically, you have vertical weld, horizontal weld, and you have a circular weld, right? And as a matter of fact, those are basically some of the skills passing the welding certificate, right? Yeah. You might be able to make good money, just to be able to hold a, not just to hold a weld certificate, but to be a proficient welder, basically. Yeah. And Canada is in short of this kind of treats people actually. Yeah. But I don't think it's good for your eyes. As you're getting old, and you probably get some sort of eye problems, if you're welding for your whole life. But anyway. This is not our concern here, and our concern is to analyze the welded joints at here, right? Yeah. But okay, I do need you to understand a couple of the concepts, particularly the next one. How do we communicate, okay, with the welder regarding the type of welds you want? So type of welds, okay, we have basically 5 different: fillet, bead, okay, plug or slot, groove, and spot. Okay, yeah. Fillet is the type of welds that we're going to focus on. Okay, I'll show you what they are. Okay, and bead, plug, okay, groove. So let's take a look at each one of the pictures here. Let me see, do I have the next one here? Yeah. So this is a fillet. Okay, so it's a kind of triangle here. Not necessarily it's going to be a triangle, but we use the triangle, and it's going to be basically on the other side, right? To represent the fillet weld. Bead is this type of thing here, okay. And this is the plug, okay, or slot kind of a weld, okay. And those are groove. Basically, you can have V type, you can have a double V, you can have this kind of V type here, okay. You can also have this U or J or bevel shape, right? So different kind of shapes. Okay. Spot weld, this is U and a J. Spot weld is like this. Spot weld is very commonly seen in automobile manufacturing process. Okay, so particularly in joining the automobile bodies. So it doesn't use any feeder material. Basically, they use the electrode on two sides of metal, cause an arc passing through the metal, so joining the two pieces of metal together. So they might be sheet metal or something else, right? Yeah. So if you're moving along the metal, right, instead of spot, it's going to be so-called sealed weld, right? It's kind of like a sealing the gap together. Okay, so spot weld. So that's the type of welds here, right? Okay, the type of the welds. Okay, the type of the weld can be used, okay, more in one or more to the type of the joints. So there are this type of joints here. So butt, corner, T, lap, or edge. So this is a butt, okay, and that's a corner. This is a T. This is the lap. And this is the edge. Okay, so type of things here. Okay, yeah. There's another picture showing what the butt is: fillet, okay, flange joint, and the corner welds. This. Okay, so weld specification. This is a part we'll look at a couple of examples here. Okay, so how do we communicate through engineering drawings with the welders here? So we use this American Welding Society specification. They basically, you'll see that the specification including several parameters such as type of weld, the size of the strains, okay, the root opening, welding process, number of spots. So basically including all the informations there, right? What you do is you'll see on the drawing there is an arrow like this and pointing to somewhere, and there's some informations on the top and the bottom of the arrow here. So those are the informations that we need to know. Okay, very basic ones. I'll show you what they are and how do we read the information properly at here. Okay, yeah. So the major one here, you need to draw a horizontal line, reference line here, and this arrow basically pointing to the joint, and then either on the top or the bottom here, those are the information that you're going to read, right? So I'll tell you what they are. So those are basically the symbols that will show, okay, at the top and the bottom here. Okay, so for example, you probably will see this or that or this or this fillet. This is the most common thing at the top of the bottom. Basically, you might see a triangle here and then another triangle at the bottom, right? Yeah. So basically, what that tells you is this is a fillet weld, right? Fillet weld. Okay. So those are basically different symbols. So for example, right? Let's see. Where's the painting? Yeah. So for example, this is a T joint here, and you have a fillet weld. So technically, the symbol should be like this. Okay. So technically, the symbol should be like this. Okay. So what does that mean? So that basically means, so as you see, there is a bottom triangle here, right? Bottom triangle. Bottom triangle refer to which side? Refer to the arrow side here. Basically, if you look at the information here, see this at the bottom of the reference line, they refer to the information is the arrow side. Okay, it's the arrow side, and top one is the other side. Okay, the other side. So in this particular case, we actually have welds on both sides, so that's why you see one triangle on the top, one triangle at the bottom here, right? Yeah. So 5 at here, that refer to the so-called leg size. So basically, it's the size of this leg. Okay, that's the 5 at here, right? Yeah. So that's the one very important information you will use in terms of the joint analysis. Okay, just remember this number here to refer to the leg size. And for this one here, and this is a circular cross section here. So basically the pipe, and we have one circle at here. So which means what? This means all around here. Okay, that means all around. And now you don't have in this case you don't need another triangle. Basically, it's just refer this leg size 5. That's the arrow. That's the arrow side here. That's this side here. Well, actually, it's all around, right? It's 5. Okay. Yeah. And for this one here, so what does that mean is you have both sides. Can you see, right? You have basically you're welding both sides here, right? Both sides. and the weld's length is 60 with a distance or an interval of 200, okay, between the two welds at here. Okay, yeah. So that's the length and the pitch. Okay. So let's take a look at an example at here, right? Okay. So what are each one of them here? So this one here, can you see that 75 on this side here, 125 on this side here, right? Yeah. And this one is 60 is the length. Okay, it's actually symmetric. The pitch is 124. Now this one is not symmetric. It's sort of intertwined together, right? So this is 60 here, and this is 120 as a pitch. So in terms of the symbol wise, right? So this is basically what you can use here. See, so when you pointing the arrow to this side here, so actually this arrow in terms of this one is which side? It's pointing to this side here, right? Pointing to this side. So that's 75 and 125 on the other side. Okay. And this is 60, 124. So that's basically 60 is the length, 124 is the pitch. So you see the two arrows, okay, on the top of each other basically means, you know, they're kind of mirrored, right? Yeah. But this one, the two things are not on top of each other, and there's actually 2 and 3, which means, well, there are 2 instances at here and 3 instances on the other side, right? Yeah, so those are basically what these symbols here mean. Okay, yeah. Okay. In terms of other things like groove weld, bevel, or V, so those are basically some other examples. Actually, you show the angles on the drawing there. Okay, so that's basically what this means here. Okay, give you the angles, okay, and they tell you the shape, right? The shape. Okay, so a couple more examples. So G grooves, okay, that's what it look like. The symbol, double-sided. Okay, so single U, starting angle, it's 30 degrees. Okay, and this is one practical from a piece of drawing. Okay, and for example, okay, there's a little flag at here, so that means it's a field symbol. So it's down in the field. Some other things, you know. Anyway, yeah. So what I want you to remember, okay, or to understand basically, is a couple of important things. Remember, this one represents the fillet weld, and remember what this down here remembers the arrow side. This is the other side. If there's a letter here, if there's a number here, that represents is the leg size. Okay, because that's a very important value. You're gonna need that. All right. So those are basically the essentials I will need you to understand. Okay. Yeah. So those are basically a very short introduction at here. Okay. Any questions? All good? Yeah. Okay. So now let's look at the welded joints here, right? And how do we analyze the welded joints and how do we design basically? Okay. As we said, we're going to focus on the fillet weld. And well, mostly fillet weld, but we'll look at this so-called the butt weld kind of things here, right? Okay. So some of the terminologies first of all, okay? So if you look at the fillet welds here, so generally you will see that this is basically what the welds shows here, illustration the welds like this, okay? Illustration of welds. So a couple of things here. In reality we actually use a triangle here, okay, to represent this fillet weld, okay, a triangle. So basically after the welds at the joint, one of the important things at the joint is going to be a mixture of the material of both this base metal and the filler material. Okay, so it's going to be a mixture material of this three things. Maybe there are two base metal, right? And then there's filler material. Okay. And there's always a little bit extrusion at here from the triangle, so that's called reinforcement, like this portion here. Okay, it's called reinforcement. Okay, yeah. And at the edges of the triangle or those trapezoid here, so we call that basically fusion area. So basically that's the affinity area between the feeder material and the base metal. So this is a base metal and this is the feeder material. So this portion here, this dashed line here is a fusion area. And same thing, this is also a fusion area, but this is not a fusion area. Okay, this is not. So what's important parameter is this, and we use basically a right triangle 45 degree, and this length set here is the leg size. Remember that the number, right? The number in the weld symbol that I just talked about. That's the symbol here. This leg size. So I'm going to use H here instead of a W. Okay, so this portion here, H, that's the leg size. So we call this is the leg. Okay, we call this is the leg here. And the other important parameter is the so-called throat here, throat. So the throat in this case, this is basically the perpendicular distance, okay, between the two dashed lines. Okay, and for this fillet material, fillet weld, the throat refer to the distance from this point to here at a 45 degree. Okay, so this is the throat here. Okay, the throat. Okay, so the other important, remember this is throat here, throat T. So you have a throat T, you have the H leg size. So now you have two area. Okay, you got two area. One is called throat area. Okay, throat area. So throat area is the area T times the length of the weld. So T times the length. Okay, so L is the length, okay, of the weld. Okay, that's the throat area. And then there's another one called fusion area. Okay, so fusion area in this case, let's say if we're talking about fusion area here, so that's H times L, right? H times L. Okay, yeah. So those are two important things that we need, particularly this throat area. Okay, so we're going to need that. Okay. 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 So now let's look at the stress. Okay. Let's look at the stress. How do we calculate the stress? Okay. So first of all, so let me show you a maybe a diagram at here. And you know what? I'll just use this diagram here. So this is the throat at here, right? This is the this throat T at here. So for this particular case, let's see if I have a force. Okay, let's see if I have a force applied at here. Okay, I've got a force applied. So what will be the stress at this welded joint here? So how do we calculate? We basically use F divided by the area. Divided by which area? Divided by the throat area here. So basically it's what? F divided by T times the total length, right? Total length. So for this one here, this is simple. So it's actually, it's a normal stress. So it's F over T times L, right? T times L. Okay. Yeah. Now, if the force is applied in a different direction, maybe this is a plate. Okay, maybe it's a plate like this. Okay. So maybe the force is actually applied in this way. Okay, maybe the force applied this way. If the force is applied this way, then the stress at the throat area is not going to normal anymore. It's going to be a shear stress. It's going to be F over TL2, right? But it's a shear stress now. Okay, yeah. So that's the for the butt weld. That's the type of the stress that you will see that it's very simple. Okay, very simple. Okay, is that good? Right. So let's focus on the fillet welds. Okay, the fillet welds. Basically, what will be the stress at the fillet welds? Examples like this. At fillet weld. So I'll show you a couple pictures first, and then we'll look at the technicality parts. Okay. All right. So here is a couple of pictures of fillet welds here. Okay. So understand that there are two types of loading here. One is called parallel loading. The other is called transverse loading. So parallel loading basically means both plates exert shear load on the weld. So if you look at these three at here, particularly look at the first one. So there are two plates, F here. There's fillet welds here. So if you look at the stress at that section there and at the bottom there, right? So both of the surfaces at there will feel the so-called shear stress, right? So F divided by a certain area. Okay. But for these two at here, if you weld it like this way, okay, if you weld it like this way, so then you apply the force. For example, here, if you look at this one, so at the bottom of this welds here, at the bottom here, right, at the bottom here, that's the shield, right? But at the other side, there, that's kind of a normal stress. Okay, so that's basically called transverse loading. Okay, transverse loading, and same thing for this one. So inside this ring at here, that's going to be this shear kind of stress on the surface, but at the bottom, okay, of this welds here is going to be the normal kind of stress. Okay, so that's another transverse loading at here. Okay, transverse. As a matter of fact, the shear stress is more of more of interest to our case at here. So let's look at this in a more first. Okay. So let's look at it in a more mathematical way here, okay? So first, more technical approach, but you shouldn't worry too much. Actually, we're not going to use the approach, just kind of illustration at here, okay? Just kind of illustration. So let's say I have basically this kind of a structure here. So we have three plates. Okay, so then we weld them together. Okay, like this. Yeah. So the question here is, what will be the stress, okay, in presence at this weld here, at the fillet welds at here, right? Yeah. So what do we do? So let's take a free body diagram. So what do we do? Let's take the top portion, this portion in here. Okay, that's this portion. So you have F at here, and then you have two F at here, and F at here, for example. Okay, yeah. So this is F at here. Okay, it's F at here. So we look at the free body diagram, and we cut a cross section. Basically, at here we cut into this welded joints here. Okay, it doesn't matter how you cut. So you cut it maybe at a certain angle. Basically, this one is the theta. Okay, so you cut it at a certain angle here. Then we look at a stress element, okay, at the cut location. Okay, the cut location. So first of all, free body diagram, in order to make it as equilibrium at the cutting cross section, you have, let's say we have a shear force Fs, we have a normal force Fn, right? So Fs, Fn has to be balanced by the F at here, so that Fs is actually equal to F sine theta, and Fn equal to F cosine theta. Okay, that kind of thing here, right? So Fs will cause a shear stress, and Fn will cause a normal stress. So that's a stress element like this. Okay, a stress element. Right? And you will see that the sigma x and sigma x is this portion right here. Okay, just a second here. Is that sigma s here? Yeah, that's sigma s. So the area is this length times the total, right? The total length here. So once you get sigma x, once you get the shear stress, plug it into the von Mises stress distortion energy theory, von Mises stress formula. You can calculate von Mises stress, right? You can calculate von Mises stress. Okay, so basically we have a von Mises stress here. So don't worry about this. We actually won't test it, but this is von Mises stress, and this is the shear stress. Okay, this is basically the tau xy here. Now remember, once you plug this into it, and this von Mises stress is basically a function what? Theta, right? It's a function of theta. And the current shear stress is also a function of theta. So let's maybe this is F1, a different function. Okay, different function. So then idea is, at the different cross-section angle theta, you will have a different value of a sigma prime or different value of shear stress, right? So at a certain value of theta, you will have what? A maximum. Okay. Then mathematically, what we can do is we can try to find at what angle of cut cross-section theta the von Mises stress will be the maximum. At what angle of theta the shear stress tau xy or tau at here is going to be a maximum. So what you do is basically you take d this over theta, actually not d, just not partial. You set equal to 0, you solve for the theta, right? So solve for theta, and then plug the theta back over here, then you get to the maximum sigma prime. Same thing for this. All right? Yeah. So I'll show you the results that are here. Okay. The sigma prime maximum, von Mises stress maximum, turn out to be 2.16 F over HL. Okay, over HL. H is the leg size. Okay, so what's H? H is basically the leg size. Okay, the leg size H. Okay, yeah. Okay, and that's when theta equal to 62.5 degree. Okay, at this much value, your theta sigma prime is the maximum. At this, and for the shear stress, okay, for the shear stress tau, it's a little bit different, and that's when theta equal to 67.5 degree, we reach this maximum there, and that's approximately 1.207 F over HL. Okay, HL. So this is the mathematical way, basically the technically, you know, how you can get the maximum value. Okay, maximum value. Okay. Now, the next one is we're actually not going to use this mathematical approach. So basically, in the actual situation or in practice, and then people find out that mathematical ways doesn't describe exactly what happens. Okay, in reality. So in practice, okay, we get rid of all the limitations of theoretical results. We use a sort of empirical or so-called conservative model. Okay, so we use a conservative model, which I'll show you next. Okay, so what's this conservative model? The conservative model is, okay, we cut it at a 45 degree. Okay, cut it to 45 degree, basically theta equal to 45. And then we get rid of that normal force. So basically we consider there is no the Fn there, there's no normal force, there's only one shear force here. And we explode that shear force to be the same as this F right here. Okay? So this is the conservative model. You see that? So 45 degree, and explode this F, okay, as this same as this F right here. So in other words, we're not considering the normal stress, okay? We're basically, by neglecting normal stress, by increasing the shear stress to give us a more conservative model at here. So in other words, basically we're only considering, okay, the shear stress. Okay, the shear stress at where? At the throat area. Okay, at throat area. Right? If you look at this one, is that a throat area? Because the 45 degree, you know, basically the length from here to here is what? Is the throat length, T, right? Throat length T. And throat area is the T times this total length L. Right? That's basically throat area. Okay? So the force divided by throat area is the shear stress, tau. Okay? Shear stress, tau. So that's the conservative model. Now, why is this conservative? Let's take a little quick calculation in it here, right? So Fs equal to what? Equal to F, right? Explode that, and the same as F. Then your shear stress, the tau, will equal to F divided by T times L. Okay, T times L. And T, if we relate the T to this leg size H, and what would that be? Because this is 45 degree, this is H, so T is what? H times trigonometry. This is H. This is 45. H times what? Huh? Cos 45, right? Yeah. What's going on here? So, yeah. It's tired, eh? I know. So, and then times L. Okay? And cos 45 equal to, I guess better not. Yes, 1/√2. So overall, if you simplify this one here, it'll be 1.414 F over HL. Okay, over HL. So with the conservative model, the shear stress is 1.414 F over HL. So now let's take a look at comparison in here. This is a shear stress here, and what's this one here? So remember, when we calculate the maximum here, that's 1.207, right? Yeah. And this, so basically that's greater than this. Welments stress at here, this is a 2.16 F over HL. Now, if we consider this one here, so here's my shear stress. So basically, you have a stress element which has only shear stress on it, right? Shear stress on it. Okay, only shear stress on it. Then what's the corresponding Welments? Welments is going to be what? √3 times the tau, right? √3 times tau. So if you have a √3 times this tau at here, and you're going to get 2.45 F over HL, right? So the Welments stress based on the conservative model is this. And if you compare this with that maximum, which is 2.16, still greater than the mathematical maximum, right? So, which means basically, that can explain why we call this as a conservative model at here. Is that good? Yeah. So always remember, when it comes to the welded joints, you are just considering, for the fillet welds here, you're just considering is a shear stress on the throat area. Okay, that's the conservative part. Is that good? Yeah. Okay, so now let's look at the different kind of situations, okay, regarding fillet weld, and what kind of a stress, how do we calculate the overall stress. Okay, so let's take a look at the first case. Okay, the first case is what I call the shear in the weld, okay, from in-plane torsion. Okay, so let me show you what we mean by in plane at here. Okay, so this is a diagram right here. So let's say try to visualize the diagram. Basically, you have a parent metal right here. Okay, and you have another parent metal, base metal right here. Okay, right. Then you weld these two together. Okay, and at the same time, so it doesn't matter how you weld. You may be welded like this. You may be welded here, 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 all around. Or you maybe just welded here and here, right? Okay, that's the next question. But the in plane, the concept here is the force. Okay, the force applied is in the same plane as the weld group. Okay, this is important because every time when I'm testing this one here, there's always people confuse this in plane and out plane situation. So the F right here, okay, is in the same plane as the weld group. Weld group meaning this is the group here. Okay, depends on how you weld it. Okay, can you see if they're in the same plane, right? If you consider this a front view, the same thing here, right? So this is in the same plane. Okay, in the same plane here. Was that okay? Yeah. Because next I'll give you another one here called outer plane. Okay, called outer plane. So this is called outer plane here. So why this outer plane here? So now your weld group is here. Okay, here's a weld group. Yeah, let's draw this. Okay, so this force and the weld group right here, right? One is here, one is here. So this force and this geometry, right? They are not in the same plane. Okay, they're not in the same plane. So now the next one, out plane here. Okay, are you comfortable with this concept, in plane and out plane? Yeah. Okay. So let's come back to this in plane right here. Okay, if this in plane and you have a weld group right here, now what kind of stress exists? Okay, or what's the basically the critical kind of value that we're looking for in the weld group here? So what we do is this: we have the force applied here, and we're looking at this weld group. So if I single out this weld group right here, okay, just for example, the weld group is like this. Okay, and this is the center, also called the centroid. This is the centroid of this weld group. So the centroid, not necessarily, because this is symmetric, so that's perfectly good, right? It's right here, so you can easily find that. You might have a sort of asymmetric weld group, then the centroid will be at a slightly awkward situation like this one, not like this. Okay, yeah. But however, you will have a table to facilitate in terms of this calculation. Just remember, this is the centroid here. Okay, the centroid. Now, this F, the effect of F on this weld group, right? Here is what you use a basically free body diagram. So F over here, then the overall the weld group, there's going to be basically a reaction force, right? So basically to balance this force F, so there will be a V basically coming up from here to balance that F. At the same time, the F will cause another one, which is what we call the bending moment, right? The bending moment, or torque, okay, which is basically will cause the torque. So the torque at this location is what R cross F. So the torque at this location is this R cross F, the T. Is that right? Yeah. So basically there should be a reaction force, the torque, to balance that one, right? Balance that one. But overall, right? Overall, in terms of the effect of the F on the weld group at here, you just have two effects. One is this vertical, basically F. Basically, there is a shear force F acting on this weld group. There's another one, which is what? This torque T, causing a torsional stress on this weld group here. Was that right? Okay. So if I draw the kind of external forces, if I draw external forces on the weld group, then I would draw basically two things. Okay, one is at V at here, and the other is T at here. Okay, so that's the two external forces and a torque on this weld group at here. Okay, now so basically in mechanics material you probably learned there's a cross section. Right, there's cross section, and then you have at the cross section you have a V. At the cross section you have a T. Right, that's overall effect like this. Okay, so now let's see, based on this V and based on this T. Okay, so now you should see that the V basically is same as F, right? Same as F, and the T will equal to what? The F times the distance from here to the location of the centroid, right? Location of centroid. So we call that, let's say call that we can call it L. Let's say capital L or something like that, right? Okay. Okay, something like this. Okay. So once we have these two information now, we're going to define, basically looking at this, looking at the weld group. Suppose the weld group is like this. Which location of this weld group is the critical location? Right, is the most critical location of this weld group. Well, what you need to understand is most critical location is basically where the shear stress is the biggest. Right, is the biggest one here. So anywhere on the weld group here, anywhere, right? If you pick any location, here, that V is going to cause the same kind of a shear stress, right? Same kind of shear. So for the V will cause so-called primary shear. So we're going to have basically primary shear. So for this case, the V is going to cause the same. So we call that tau prime. So V over the area. Okay, V over the area. The area here refers to the throat area. Okay, the A is the throat area. Okay. So in this case here, how many throat area do I have? I actually have a throat area at here. We have another throat area at here, right? So I've got two throat. Basically, the A at here, we call that the total. Okay, total shear area, or basically total throat area. Okay, yeah, that's the A there, and the V is F, right? So it doesn't matter, really doesn't matter if where and here, or here, it's the same. In this case, the tau prime will be the same thing, right? The tau prime is the same thing. Now you have also the torque T at here. So in shaft design, when we learn shaft design, we have a circular shaft, and if we look at everywhere on the edge, we actually have the same kind of a shear stress, right? Same shear, which is what? TR over J, right? TR over J. But in this case here, the cross section, it's not a circular cross section. The cross section at here is this. Right, is this. So basically means what? Your calculation of a shear stress due to the T, so your shear stress due to the T is still TR over J, right? It's still TR over J. So this one here we call the secondary, the secondary shear. The secondary shear, still TR over J, but you can see now the R determines the value of tau prime, right? Because J will be the same thing. J refer to what? Refer to this polar moment of area of this weld group. Okay? Is that okay? Right. So you right now it's this, right? You might have a box. Maybe you have a circle, right? Maybe you're welding a pipe. Okay. So basically, the J here is the second polar moment of area here. Okay. But the R is what? Is the distance from the centroid to the location. Okay, to the location that's interested. So if you look at this geometry right now, the geometry right here, apparently which location? This location give you the maximum R. That makes sense? Right? So that's why the critical location for this weld group we're going to analyze is this location here. So okay, that's the most critical location for this particular case. Is that clear? Okay? Yeah. So the other thing that you also need to be affirmative or very comfortable with this is this. What's the geometry relationship between tau double prime and the T? So this is basically, make sure you knew how to draw this tau double prime. You draw the R here. So the torque T goes like this, right? So it's like you have a torque over here. So the tau double prime will be in the same direction as the T, the torque. Okay, and basically the tau double prime is perpendicular, okay, to this R at here, okay, to this R. Is that good? Okay. So now this is how you draw these two shear stress. They are like two vectors. This tau prime primary is due to the V, that's going down. Tau double prime, that's due to the T, and that's perpendicular to the R. Okay, perpendicular to the R. Then overall, the tau is the vector addition of these two at here. Okay, is the vector addition. So the shear stress tau, right? That's basically okay. So basically, the absolute value of the addition of these two give you this tau there. Okay, give you the tau. Is that clear? Okay. So now you probably wonder now. Okay, so now I probably need a little bit of trigonometry. So it depends on the situation. How do I calculate the tau here, right? You're gonna have to base on this and that, you know, certain angles, and then right. So that's probably what's happening. But you do have a little shortcut at here, okay? Particularly when it's this kind of geometry. So what you do is this. So you look at this tau double prime, right? Look at the tau double prime. You can always decompose the tau double prime into two portions, right? So there's one over here, and there's another one over here. So maybe I'll draw it here. So if this is the tau double prime, then the tau double prime basically always has two components. One is this, one is this, right? So the top one here, let's call that the tau x double prime. Let's call this tau y double prime. That makes sense? Okay. So instead of calculating tau double prime as we said is a tr over j, right? Tr over j. Maybe I can just calculate tau x double prime and tau y double prime. And then what? And then you see the tau y double prime in the same direction as the tau prime here, right? The tau prime. So tau prime is the same direction, right? In the same direction. So the overall tau will equal to what? Square root tau prime plus tau y double prime square plus tau x double prime square. That makes sense? Right, so the geometry wise, you see, if I give you, say, okay, here, look, here are two vectors. give me the vector addition, right? So I think it's not that easy to calculate. You need to have the angles first, then use some law of cosine to get the vector addition, the magnitude. But now, if I can get this and that, okay, and this, because those are 90 degree at here, okay, 90 degree, so I can use this simple formulas here to do the calculation, right? So the question here is, what will be the tau x double prime and what will be the tau y double prime? So tau x double prime is the shear stress, okay, in this direction here, right, in this direction. Now remember, which one caused the tau x double prime? T, right? So T caused it. So what's the distance between this tau x double prime and the vertical line is what? This portion, right? This portion. Okay. So let's see, which one did I call it? I call this is x. I call this is x, right? And I call this is y at here, right? This is y here, y-axis, axis. So maybe this in terms of reference coordinates, and this is x, this is y, knows, right? Yeah. So basically, geometry-wise, okay, if you look at this diagram there, your tau x double prime will equal to what? T times this portion here. So that portion is actually what? Let's say maybe this is basically the centroid, the y coordinates of the centroid, right? The y coordinate centroid. So you can just use the t times, let's say maybe y bar divided by what? The j. Okay, so that's the tau x double prime. And then tau y double prime will be tx bar over j. Okay, so is it easy to find x bar, y bar? Yeah, if this is symmetric, you know, the geometry, right? It's very easy to find this x bar, y bar, right? What's y bar? And this little portion is y bar, right? This portion is y bar. Okay, yeah. So this is basically how you're going to get tau y double prime. Okay, maybe no, sir, that's x bar. X bar. This is which I call that x direction. So x direction, y. Yeah, this is x bar, right? This is x bar here. That's right. Okay, so geometrically you use this to get this tau double prime, okay, and tau x double prime, tau y double prime, combine with tau prime to get the tau here, okay, to get the tau. Was that good? Okay, so now the last point to make is the j. So how do I get the j then, right? The j is a second moment of the second polar moment of area. So technically you had to go through double integrals and things like to get the j. So what we do is, okay, to save us trouble, we use a table from our textbook. Okay, where's the table? And that table, let's just open it up here. Is table 9-1. Okay, so 9-1 at here. So let me explain how you use the table at here, okay? How you use the table. So maybe I'll just write down here. So we use table 9-1 for j, okay, for j. Now you got to be careful at here, okay? You only use this table for the j because we have another table 9-2, and that's going to be for the I. What is the I again? Second moment of area, right? This is the polar moment of area, okay? Yeah. So for this table, okay, number one is they are considering it's a unit through area, unit through length t. So here basically you see that it just drawed a line at here, right? Just draw the line. So remember when we do analysis, we have the T at here, right? We got the T here. So then T times the L is the area, right? It's the area. So in that particular table, they use a T as sort of a unit list, just unit 1, right? Unit 1. So what's the actual T? Then you have to multiply certain things, right, to get the actual values, all right? So in this table, it's just a line here, okay? Just a line. So let's see, how do I read it? Let's see, this is okay. What I have it here. Maybe I'll just draw a couple of them here to include. Okay. So for example, we have 2 vertical bar at here. Okay, 2 vertical bar. Now this diagram shows you what the X bar is, what the Y bar is. Basically tells you the average, okay, or the centroid location based on the dimension of the D and the B. So D is the length at here, B is the gap between these two. So X bar is half B and Y bar is D over 2, right? Then the J, it give you, this is not the J. What it give you here is called a unit polar moment of area. So this is there's a U here, right? This is called, okay, unit, okay, polar moment of area, okay? Okay, polar moment of area. It's a JU. So JU is this quantity here. And if you're interested in how JU is derived here, look at my lecture notes. There's one page I kind of spend the time is to derive this one here. Okay, so if you're interested, you can look at it how this is derived here. So every one of them, right? Every geometry, there's a JU. Okay, there's a JU. Then what is the J then? Right? What is the J? So remember, this is a unit list here. The T is set to 1, right? Set to 1. So what do we do? Basically, when we calculate the J equal to 0.707 H. This is basically the T value, the actual T value. Remember that? Right? The T is the throat length, the throat basically T. And T is related to the H, 0.707 H. You know, H cosine 45 degree. So then times the JU. Now that's the J there. Okay? That's the J. Is that good? Yeah. So be careful with this thing here. Okay. Every time I see different mistakes being made in terms of using this table right here. Okay, that's J. And this table also tells you the total throat area. This A here is the total throat area. Okay. See if that makes sense or not. So what's the total throat area? Total throat area is the length D times what? Times T, right? But you have a 2, so you should times another 2. So basically T is what? 0.707 H times D times 2, which is what? 1.41, technically there's another 4, HD. Make sense, right? Yeah. For this one, you can verify again. You know, if this is A is this, or if G is this, or X bar, Y bar is like this. Okay. Yeah. Now that's how you interpret this table 9-1 and here, right? This is very important because if you interpret it wrong, and you will end up with completely wrong results, though, huh? Yeah. So let me give you an example right here. As to properly interpret these things here, okay? Right, there's another question in here. So let's see if I have a weld like this, right? This is a 2 horizontal. But if you look at this table 9-1, if you look at 9-1 in here, and up going, and then there's one more basically circle, there is no 2 horizontal bar or that kind of weld. Why is that? Yeah, exactly. So which one actually you're going to use? This one here, okay? Because it's a polar, right? Because it's causing rotation. So basically, the G for this and G for the 2 horizontal is the same thing, okay? It's the same thing, okay? Yeah. So let me show you an example right here. So let's say I have a 2 metal piece, okay, and then we weld them together, and here is the welding information. Okay, there's welding information, and this is 2, this is 2, this is a 6, okay, like this. So let's calculate the stress at the critical location. Okay, let's calculate stress at the critical location. Then next lecture we'll look at the strengths there. All right? Yeah. So if I calculate the stress of critical location, and first of all you got to basically look at what does the weld group look like? What's the geometry of the weld group, right? So basically, where do you get the information from? This symbol here. So basically, what's the weld group look like? The weld group meaning you have portion at here and portion at here, right? Okay, yeah. So in other words, you have you can draw 2 lines like this, okay, to indicate this weld group like this. And as actually in an example we showed, the critical, first for this centroid, the critical will be right this location at here. Okay, will be this location. Okay. Yeah. So if I relate this to the diagram that we have it here, this is a 2 vertical one here. So if I rotate it according to the dimension, and this is a B, this is a D, right? This is a D here. Okay. Yeah. So what you need to be careful here is basically this one here is actually good because it's 2, so you probably won't make a mistake even you mixed up this B and a D, right? But if I change this to maybe, I don't know, 2, maybe change that to 3. So what's B, what's D? Let's say this is 3 here. So what's B? B equal to what? To 2 or 3? To 2. D is 3. Okay? D is 3. So let me use this one for example here. Okay? So now let's calculate. Okay? Suppose that we don't know the F. We'll keep the F as an unknown value at here, right? So first of all, what's the V? V equal to F. And then what is the T value? F times how much? 6, 7. So what should be the F times what? F times the distance to where? To the centroid, right? To the centroid. Let's use a 3. 7. Okay, very important. Okay. Oh, sorry, 7.5. Yeah, 7.5. Okay. Yeah. So then, at that location, first of the primary shear, tau prime equal to V over A equal to F over the total throat area. So what's the total throat area? So you can look at this table right here. This value here, right? This value. So that's 1.414 times H times D. So what is H then? Which one is H? Huh? That guy there. Okay? 5/16 times D. D is 3. Okay? Yeah. Okay, so that's primary shear. Then tau x double prime, secondary shear. Okay, secondary shear. So I'm looking for basically tau x. This is tau x double prime, and tau y double prime. Okay. Then we have tau prime, right? That's the decomposition. Yeah. This is the leg size, H. Right? Yeah. Is that good? So if you go back to your typical drawing here, this is H. Okay? Yeah. So what is the tau x double prime? Based on the geometry here. So that's a T times R times over J. So the question is, what's R? R is which one? Is this, right? Is this. So what's this distance? Go to the table. It's this one, x bar. X bar is what? B over 2. Okay? Now what is the J? 0.707 H times JU. And what is JU? Here. That's how you use the table here, okay? So then in the table here, substitute the D and a B property. So D is 3, B is 2. And so you can do a calculation yourself, right? Yeah. Then what about the tau y double prime? That'll be what? T times tau y double prime, this quantity, so times this distance here, right? This distance. And that distance, according to the table, it's this y bar here, right? It's y bar. Okay. And that's D over 2. Okay? Over G. So then overall, your tau is tau prime, tau y double prime square, tau x double prime square. Okay, like this, to do the calculation. Was that good? Okay, so let me show you another one here, probably more complicated. So let's say I have a 2 plates. Okay. Now this time the weld group is this. Okay. That's where you do the weld. Let's say, suppose that what's the leg length? Yeah. Anyway, so let's suppose there's a certain leg length. That's not the point. I just want to show you how to use a table to calculate the primary and the secondary shear, right? Yeah. Okay. So you have a force F over here. Okay. There's a certain number of F. Okay. Let's just say this side here is 10 and that's 5. Okay. That should be enough. Okay, so if this is the weld group, and let's find what's the critical location. So what do? We can draw the geometry, right? First draw the geometry out. So when you draw the geometry out, I think the best bet is to go to the table. Let's look at the table here. Which one are we gonna use? This one here, right? This one. Okay. So if you look at this one here, that's basically the same kind of a geometry. Okay. Same kind of geometry as this showing here. This one showing here. So basically your centroid is somewhere over here. Okay, centroid is here, and this is X bar like this, right? This is X bar like this. Okay. See, the trick here is to make use of information to calculate what you want here. Okay. So first thing is, what do we need? We need to know basically the V, that's same as F, and then we need to know the T, right? The T here, the torque. And the torque equal to how much? F times the total length from the distance from the location F to the location centroid, right? The location centroid. So if this is a 5 here, let's see, and let's see if this is let's say make it a little bit more difficult. Let's say this is another 5 here. Okay, it's another 5. So what will be the total distance from F to the centroid? How do I get that information? Come again? Exactly, yeah, 10 minus x bar, right? Yeah. So 5 by 5 plus 5 minus x bar will be the distance, right, to the F. Okay. Where's x bar from? Here. Okay. So there's nothing tricky, just plus minus divisions, right? Yeah, but you had to read the table properly though, huh? So that's F 10 minus x bar. Okay. Then the next thing is critical location. Where will be the critical location? Apparently, I think the critical location is still here, right? Still here. If we're looking at the critical location in here, your primary shear is still V over A, and A is this. Okay, and A is this. So the tau x double prime is going to be what? Is going to be T times which portion? This portion, right? This is tau x double prime. This portion is actually half of what? D. Basically, it's the y bar here, right? The y bar. So divided by J. Okay? That makes sense? Yeah. Well, yeah, a more tricky situation is the y bar is not half of the D, so you have to be right? But yeah, I don't think they're going to trick you like that, right? Yeah. So lastly, tau y double prime is going to be how much? This is another one there. T times what distance divided by J? T times which distance? Yeah. Right? This distance. So that distance is actually how much? 5 minus x bar. Okay? Was that good? Yeah. Okay, so we'll finish this in the next lecture, and then we'll have one little thing on the screen. So that'll be it for this term.